Hello everyone. So statistical thermodynamics is almost complete. Okay, now few more things are left. One of them is molar partition function. So in a very precise manner I am going to discuss this thing. Okay, I think you should know about this thing, molar partition function. You know, each particle has its available energy levels, isn't it? And this is F, and if there are two particles, okay, then the combined value of their energy levels should be F square. Okay, if F is for one particle, then for the second particle also it is F, and it is a multiplicative property. It should be F square. If there are three particles, the available energy level should be F cube, and if there are n number of particles, it is F to the power n. If this F is n0, then this is F to the power n0, and this is known as molar partition function, and we have to relate them with classical thermodynamic functions. Okay, so this is the topic of our today's discussion, molar partition function, which is denoted as Z. Okay, capital Z. So if there are total n number of particles in a system, then the number of moles n equals to n by n0. Definitely n by n0 is the number of moles. If you have 32 grams of oxygen, then what is the number of mole of oxygen? It is 1, because the number of particle in 1 mole of oxygen is Avogadro number. Avogadro by Avogadro is 1, so 1 mole. If you have 64 grams of oxygen, then it is 2 mole. So if you have n number of particles, okay, then divide them by the Avogadro number, then you will get the molar expression. That means 1 mole, that means 1 gram mole, 2 gram mole. So this n is nothing but gram mole. Okay, and n0 is the Avogadro number, and small letter n, actually in our gas chapter, okay, we express the number of moles as small letter n, but here it is actually the number of particles. Okay, this is not the molar expression, this is the number of particles, this n. So this number of particles is nothing but the number of the gas molecules present in the system, and if it is 1 mole, then this n is nothing but n0. So in that case, you have n0 number of particles, and therefore their combined number of available energy states is F to the power n0, and this is nothing but expressed as Z, which is called the molar partition function. So this is a very easy thing, and you can easily relate this Z with the expressions of the classical thermodynamic functions. Okay, so for 1 mole of a substance, n should be replaced by n0, and the corresponding thermodynamic expressions would become, look, how easy is that? U equals to what? Nkt square dln by dt. In place of n, you are writing n0, so n0 kt square dln by dt, and this n0 would go to the power of f, isn't it? Because this is logarithm. Okay, so any coefficient of any logarithmic term should go to the power, okay, of that thing, of what you are taking the log, isn't it? So you are taking the log of f here, so it will go to the power of f. So simply it would become d ln f to the power n0. Okay, so and what is f to the power n0? F to the power n0 is nothing but z. Okay, so this is simply kt square d ln z by dt. So for our convenience, we have introduced this term z. Okay, so same thing can be done in case of s also. So this color difference, this is red, this is magenta colored, this is also magenta colored. Okay, I don't know what is it appearing in your device, but in my screen, in my monitor, it is appearing as magenta, not red, it is magenta. So anyway, it means u equals to this one. This is the final expression. So I haven't written it in a separate box. You can do this in a separate box. Okay. So along with the derivation, the final expression. Okay. Now in terms of S, in case of S, nk ln f, nkt dln by dt. Replace them by n0, then send them to the power of f, and then convert them into z. So it becomes finally k ln z plus kt ln z by dt. Okay, done. Expression of A, nkt ln f, final expression minus kt ln z. I'm not just discussing it in details. The expression of P, nkt del ln f by del v at constant t. The final expression is kt del ln z by del v at constant t. And the expression of G, nkt minus nkt within bracket ln f plus del ln f by del ln v at constant t. And the final expression is minus kt within bracket ln z plus del ln z by del ln v at constant t. Okay, so in your exam, whatever be the term, it may be f or it may be z, you can easily do according to the requirement of the question. Okay, if it is given in partition function, then use the terms in terms of f, or if it is given the molar partition function, then use z. Very simple. So in this context we have two more. One is H, which has the final expression kt within bracket d ln z by d ln t plus within bracket, not within bracket, actually it is at constant temperature, del ln z by del ln p. Okay, and for Cv the final expression is k within bracket del t of t square del ln z by del t at constant volume. Okay, so I haven't just read them in details because all the steps are same. Just replace n by n0, send it to the power of f, then instead of f to the power n0 you just put the value z. Okay, so take the screenshots and take the note. That's all. Thank you. Have a nice day.